If you've ever had an interest in working with computer architecture, or maybe even writing an emulator for something that you liked in the past, or maybe even now, a Chip8 emulator is a really good place to start for that. My main goal of this series is to focus on building a Chip8 emulator from the ground up using C and explaining every bit of my process along the way. This isn't going to be focused on beginner-oriented things, but I'll try to explain as much as I can. If you're familiar with data types, arrays, functions, things of that nature, you should be able to follow along okay, even if C is not your first language. If people end up really liking this series and they want to see more of what I do, I will definitely consider doing a beginner tutorial, so let me know what y'all think. Anyway, let's get started. Starting off, I made this visual aid sheet that I think encompasses the Chip8 architecture decently. If you have a look here, this is our CPU, and this is the main thing that we're going to be focusing on for a bit. The registers that we have here range from V0 to VF. That means that we have 16 registers since hex is 16 base. So our registers will go from 0 to 9, A to F. And the flag register is actually going to be VF, so it's pretty easy to remember because it has F at the end. This register we're going to be using for our flags, which will be important later in our opcodes. Index register is just a place, basically a pointer in memory, and then program counter is our location in the ROM that we are currently running. In the CPU we have a 16-bit stack. This stack, all it does is hold return addresses for when we're jumping to different subroutines in the code. We have a delay timer and we have a sound timer as shown here, and we also have a stack pointer. Stack pointer basically just lets us know where in the stack we are currently located. It'll make more sense as we go along through the code, but this is the general synopsis of the Chip8 architecture. Now if you look down here, this is the same setup for our registers. We have our 16 from 0 to 7 here, from 8 to F, and our carry flags are going to be here in VF. Our special registers are here, and our memory map is here. Our memory map is really important because it tells us where things for the Chip8 are going to go. For example, at X200, hex 200, our program ROM starts here and encompasses the rest of the memory up until the final bit. The Chip8 is able to address 4 kilobytes in size, which is 12 bits. If you take a look at 050, the font set will load into here, and we'll get into that here in a moment. But basically the Chip8 has a font set which is just an array of hex values that make up the fonts that it will show on screen. Okay, let's get started. We're going to go ahead and make a new file. We're just going to call it cpu.header. We'll go in, and first thing we'll put in our header guards before I forget, because I have a habit of doing that. Okay, for our includes, we're going to need to add our standard int header for sure, and we're also going to need to include the standard bool library. This will make a bit more sense here in a bit, but the reason why we're adding these libraries, the standard int is important because we're going to be declaring 8-bit unsigned integers and 16-bit integers. We're going to need the standard int header to do this. Okay, so let's go ahead and make our CPU structure. I'm going to start off with typedef struct CPU, or we'll do Chip8 CPU. And then on the bottom here, we'll say CPU in all caps. What this does is the structure is actually called Chip8 CPU, but the typedef allows us to use CPU everywhere, so we don't have to type out the entire thing each time. There are different ways of doing this, but this is how I'm used to doing it. First off, we'll start with the registers in memory. I'll just make a comment here just to make things easier. We'll start off with our register array, V16. So since the registers start with V, we'll just call it V. And we know we have 16 registers, so we'll just make the static array of 16 elements. We'll also make another array, which is just going to be called memory. And we'll say memory size. And we'll go ahead and define that up here. Say define memory size is 4096. So the reason why it is 4096 is, as I said earlier, the Chip8 can allocate 12 bits of memory in its map. So 12 bits is the equivalent to a maximum of 4,000 bytes or 4 kilobytes. 4096. So we'll go ahead and move on. We'll make a 16-bit integer called IDX for index. You can call it just capital Y or capital I if you want to, but I honestly like putting IDX because then it just looks easier to understand for me. You went 16 PC for program counter, and that should do it for the registers and memory portion. From here, we'll look at the stack. For the stack, we have 16 elements, as I mentioned before. Stack 16, and then we have our stack pointer, which is an 8-bit unsigned integer. So next we can do our timers, but before we do that, I'm actually going to do the inputs here. So the Chip8 uses a 16-button keypad. I usually just call it bool keyboard array of 16. You can call it keypad if you want to. I just called it keyboard in pretty much every code that I've done this for, so I'm just going to leave it as keyboard. We have 2 timers, 8-bit delay timer, and 8-bit sound timer. The delay timer is going to be used for how many times the Chip8 has to update on screen, and the sound timer is going to be used for every time the sound needs to be updated. Pretty self-explanatory there. It'll make more sense once we get closer. And then last, we'll also allocate the frame buffer, which is what we're going to use to pass all of our video information to. And we'll call it normal buffer inside the array. And I'll show you why in a moment. When we go up to here, we're going to go ahead and define this. Define normal buffer. And the normal Chip8 buffer size, or video size, render size, is 64 times 32. So 64 bits wide, 32 bits long. Now, the reason why we're defining this is because there's actually a second buffer for a high-res mode. And the high-res mode will use a buffer size of 128 by 64, which is essentially double. 128 bits wide, 64 bits high. So we're not going to do anything with this just yet. We will probably make an if-def for this, but for right now, I just want to leave it here so you're aware that there is a high-resolution mode that we can implement into our code later on. But for now, we're going to start with the normal buffer because it's the easiest to implement. Okay, so now we're done with the actual CPU structure, but what I want to do now is I want to add 2 variables for proper operation of the CPU. And the reason I'm doing this is because there is an instruction in the Chip8 instruction set that forces the CPU to halt until a button is pressed. Now, the reason why we need these variables is because we need to be able to store the address of where we're at so we know where to continue from. And we need a variable to tell us when we're halted. So we'll do halt until pressed. This will come in handy later on, but for now, just be aware that these 2 are just meant for when we pause our CPU. Okay, our structure is looking pretty good. Since we're here, I think we should add our helper functions on the bottom. So what we're going to do is our main one is going to be void CPU initialize, or just CPU init in this case. And and we're going to pass along the pointer of the CPU structure. We're going to do the same thing for the next function, which I'm going to call fetch opcode. Now the difference here is the return type is a 16-bit unsigned integer, and the reason for that is because every address point is a 16-bit unsigned integer, so we can pass that back. The opcodes are also 16 bits. So our program cycle is where things are actually going to be incremented and updated. This is going to be like the actual heart of the program. And then our next one, we will do void exe opcode. And for this one, we will pass along the pointer, but we'll also pass along our opcode. So our opcode that returned from fetch opcode, we can now send into this function. Lastly, we'll do an update timers function because we will need that later. Okay, so you may be wondering why I'm doing it this way. If you have a look at our visual aid here, I went ahead and added on the bottom our fetch, decode, and execute cycle. So this is the way that CPUs work in general. You have a fetch, decode, and execute cycle. So when the fetch is called, it will find the opcode that we need. The decode will then decode which opcode it is and what are the variables that were sent with it. And then execute, which is doing the actual arithmetic of the function, or the opcode rather. So PC, which is our program counter, will then be incremented by 2 unless the opcode jumped. And then we will return back to fetch, decode, and execute based off of whatever the pointer value is at that moment. So that is why we have a fetch opcode, program cycle, execute opcode. That is because we need to have our logic in these functions. The void exe opcode function is most likely where I'm going to be putting both the decode and the execute, because we are going to need to do both at the same time for it to be easy for us to manage. Alright, so now what we can do is we can make our actual cpu.c file and we can go from there. First things first, we'll include the header file that we just made. And we'll start with our initialize function. So void cpu initialize cpu pointer cpu. And this is where we're going to initialize the entire CPU structure at, as if we're just turning on a computer. We need to make sure everything is initialized properly, otherwise we're going to run into some weird errors. So we're going to start with this. First things first, we'll start with the memory. And what we're going to do is we're going to set every single register in the Chip8 to 0. So the easiest way to do this is a memset. I'm going to go ahead and write memset CPU pointer. Inside, we're going to take the V array. We're going to set it to 0, and it's going to be the size of CPU V. In order to use this, we actually need to include a different file. So what we're going to do is go over to here, code completion, string.h. So what this does is it just sets every element of the array equal to 0. You can do this using for loops if you want to as well. Memset is generally faster, but if you just prefer for loops, like I know some programmers do, have at it. I'll stick with memset just for the ease of readability, especially for people who haven't done this before. CPU index is going to be 0, and then CPU PC. So this one is going to be what I had mentioned earlier, where our program counter starts. So our program counter starts at 0x200. And if you have a look again at the visual aid that I made, we'll go down to the memory map. And if you have a look here, 200 is where the program ROM loads into the actual memory. So that is why we set that equal to hex 200. Next, we'll go ahead and do the stack. We'll also do a mem set here. We're going to take the stack, set it to 0, size of the stack. We'll take the stack pointer and we'll initialize it to 0 since it hasn't been incremented yet in the code. Next up, we'll do the timers. CPU delay timer equals 0, and then CPU sound timer equals 0. We'll do the same thing with the input, which is going to be another mem set since it's an array. And then from here, we'll also do the font set. Now, the font set we have not actually put into the header yet, and we are going to get there, but I want to write this code first so you understand what we're doing. The font set we mentioned earlier in the memory map that it starts at hex 50. So what we're going to do is we're going to declare on the top, or define rather, the actual location there. Font set location is 0x050. And while we're at it, we'll actually go ahead and fix this for the program counter as well. So define program begin, and we'll say 0x200. So then from here, we will take this code and we will put program begin. And then down here, we will take our mem. We're actually going to do a mem copy this time. And the reason why is we're going to be copying the font set into this location in memory. And I'll show you the font set here in a moment. We're going to go back to the header file and insert that. So for mem copy, we'll do CPU memory plus the font set location. So we're exactly where we need to be. Font set, which we haven't defined yet, but don't worry about it. And then size of font set. Now, of course, it's going to say undeclared identifier. What we're going to do is we're going to go back to our header file and we're going to copy over the font set. Now, this is the same font set across anything Chip8 related. So I will leave this code in the description so you can just copy it for yourself so you're not having to type the whole thing out. But if you were to search up the font set, this is going to be exactly what it is. And I made sure to put the actual values here on the right of the font set. So this is an array of 80. So when we pass it into mem copy, it should work just fine. And there we go. So now it is working properly. And what we're going to do to finish this initialize function off is we're going to set the other two variables that we made, the helper variables, to 0 and false respectively. So the wait register will set to 0, and then CPU, the halt until press, is going to be equal to false since it is a Boolean value. Okay, I'm feeling pretty good about this setup so far. I'm thinking that everything that we need to get something solid started is here. If you have any questions about this, please leave them in the comments down below. I would love to help you out. I really hope that you're learning something from this, and hopefully in the future parts, we can go through more of the fun stuff such as getting the opcodes ready, loading in our file, and getting ready to hopefully load a game. I appreciate you all coming, and I hope to see you in part 2. Have a good one.